Hello there, welcome to the Learning of Engineering tutorials. In this video lecture, we will see the composite material when it is exposed to the thermal stresses. As you know, the temperature variation is quite common. It depends on the seasonal situation also when the member is going to be exposed to the environmental condition. But some cases, they are deliberately, it's exposing to the thermal stresses, right? Suppose you can take it the furnaces or the liquid molten metal carrying the ladles also, they are going to be subjecting this kind of stresses. You can take the IC engines, their blocks are going to be IC engines, the heat generation is there. That means the chemical energy is converted into the heat and that converted into the mechanical work. So in that process, all the devices are going to be subjected to the thermal stresses. And we need to go with the proper analysis of that, and how much thermal stresses is going to be building, and what is the behavior of that material, and what type of material can capable to take it. You can take the aerospace engines, so there the high temperatures are going to be generating, like 700 to 2000, 3000 degrees also going to be generating in the rocket engines. Then those materials also exposed to the high temperatures. Then what happened? So the single materials are not going to be valid. So then what we are going to do? We are using the composite materials. There is going to be steel material or aluminum is going to be supposed there. They are going to be using the ceramic coating like alumina or zirconia or this kind of the ceramic materials they are coating. So due to this reason, the ceramic materials are highly sustainable to the high temperatures. So then automatically it is going to be sustained for the specific application. So here is the example for that. So thermal stresses in a composite bar. There we can see I have taken the two materials. One is the S is going to be belongs to the steel. This is the ductile materials, and B also the brass material. This is also ductile materials. There we can see I have given with the different hatching. So now it is at the room temperature. Then I made to subject it to the temperature gradient. So then when the temperature is going to be increases, so then what will happen here? So as we know, the brass thermal coefficient is going to be much better than the steel. So then automatically when I am going to be allowing for the free expansion, the brass material will going to be elongating and the steel also going to be elongating. Because of the thermal, that is the coefficient of linear expansion is more in the brass material, then elongation is going to be much better compared to the steel materials. And when it comes to here, the steel thermal coefficient is going to be very less, and according to that it will expand. But my case is, I don't want to allow for the free expansion of the member. So then what I am going to do, I am going to be sticking these two materials. Suppose this is going to be the steel material and this is going to be your brass material. Then what happened? I am going to be sticking these two very tightly. Then I will try to exposing to the temperatures. So then what will happen? So can you see the brass and the steel are going to be parallelly, they started to expansion is going to be taking place. Because even though they existed the different thermal coefficients, then how this is going to be mechanism is happen. Can you see when the brass is going to be trying to move in this direction, right? It is trying to move in the upward direction, and there is going to be a contact we are going to be established here. So then what happened? The brass is trying to pull the steel material along with that one. It means that the steel is going to be subjected to the tensile forces because there is a binding is there between the brass and the steel. So then what happened? When the brass is start elongating, it is also trying to pull the steel material in the same direction. Right? So then the steel material is going to be subjected to the tensile force. And similarly, the steel also has its own thermal coefficient of expansion. So then what happened? It is going to be less than the brass. So this elongation is going to be slower side compared to the brass. So then what will happen? The steel material is going to be trying to pull in the downward direction. Right? So the free expansion of the brass is not happening. Right? The free expansion of the steel also not going to be happening. That's because of here, these two are going to be binded. The brass is exerting on the steel is going to be the tensile force, and the steel is exerting on the brass is going to be your compressive force. So due to these reasons, they are going to be developing at the, that means they are going to be elongating at the same length. So there we can see some terminologies here. AB is nothing but the cross-sectional area of the brass material, that's circular, square, whatever it may be. Next, sigma B is going to be the stresses. This is called stresses in the bars. And EB is going to be thermal strains. And alpha B is the coefficient of linear expansion of the bars. That is the brass. and Young's modulus is going to be EB we have taken. The same terminologies we have taken for the steel also. AS, sigma S, ES, next alpha S and ES are going to be the respective parameters for the steel. And the T is nothing but your temperature gradient. Now we need to find out what is the load is going to be acting on that system of the steel as well as the B. We know this member is going to be subjected to the tensile and this is going to be the compressive. Then how could you calculate that part? So there we can see the PS is going to be the load. We know the stress is equal to load by area. So now I am going to be writing sigma S into area I am going to be taking, AS. And similarly, the brass material also subjected to the load, PB is equal to sigma B into AS I am going to be considering. We know the load acting here on the tensile, that means in the steel, and the brass is going to be the equal. Then only the equilibrium condition is going to be achieved. That is the PS is equal to the PB formula we are going to be writing. That is the load on the brass is equal to load on the steel. So that's going to be sigma S AS is equal to sigma B by A. B we are going to be writing. This is the B. So this is the way we are going to be developing the equilibrium equation between the thermal stresses. So now I am going to be comparing with here with the strain also. We know the free expansion of the brass, when we are going to be making the composite, it is not happening. That means it reduces the certain elongation of that material. So now I am going to be considering that I will develop that equation. So now we are trying to find out the actual expansion of the brass and actual expansion of the steel. We have developed that mechanism. We understand one member is going to be subjected to the tensile force, one is going to be subjected to the compressive force. And due to this reason, that materials are going to be start to grow in the same length. So now that is actual expansion of the brass that is equal to actual expansion of the steel. Because we are assuming that del S is equal to del B, that is the expansion suppose. So then how to calculate here? I am going to be trying to calculating the actual expansion of the brass that is equal to. We know the free expansion of the bars is equal to how much? That is the free expansion is equal to alpha TL is going to be the free expansion of the bar. And similarly, the contraction due to the compression stress induced in the bar. So that I am going to be writing over here. So that is going to be, here I am going to be writing sigma B by EB into the L, that's we have seen in the previous video lecture. So now I am going to be equating over here. So that is going to be del LB is equal to alpha TL minus sigma B by EB into L we are going to be considering, right? So this is going to be the actual elongation of the brass. And similarly, we will try to find out the actual expansion of the steel. If I am going to be taking, that is going to be del S. Del S is equal to, same we are writing, the free expansion of the steel that I am going to be writing here, this is going to be the B, right? And this is the LB, suppose if I am going to be taking. So then that is equal to the free expansion of the steel, that is going to be alpha S T into LS we are going to be getting. And similarly, actually, due to this tensile load acting on that steel because of the brass, it is going to be elongated more than that I am going to be taking the place, that is because of the load of the tensile. So that I am going to be taking here sigma S by ES into the L we are going to be considering. So here is going to be EB we are going to be considering. So can you see, this is going to be the actual expansion of a steel. That's because of the thermal stresses and because of the tensile forces. And here also, this is because of the thermal stresses and this is because of the compressive force acting on that material. Now I am going to be equating these two. So that how we are equating? That's going to be del LB is equal to del S we are going to be considering. So here we can see that's going to be del B, that is the expansion, actual expansion of the brass, that's going to be alpha B T LB minus sigma B by EB LB we are going to be taking, that is equal to the actual expansion of the steel. So that is going to be alpha S T LS plus sigma S by ES LS we are going to be getting. So from this equation, we can find out what are the parameters we actually required, right? So this is the way when the thermal stresses in a composite bar, the behavior of the material we can calculate from this one. A single material behavior is different. When the two materials are going to be combined, its behavior is going to be different. So this is going to be the mathematical model where we can analyze such a behavior which is going to be contracting and which is going to be expansion. And due to this contraction, what is the mechanism behind to reduce the free expansion of the system? So this way we are going to be calculating. Suppose you can take the thermocouple. Thermocouple also one of the best example for the thermal stresses induced in a composite bar. There we are taking the two different types of the thermal expansion, the materials. So in this case what will happen, most of the time thermocouple we are using to measure the temperature differences or temperature gradient. So then in this case what happened, one material is going to be trying to elongating, another material is going to be the less coefficient of expansion. High coefficient of expansion, low coefficient of expansion. So then because of this one, so there is going to be a circular form is going to be generating. Right? So this way we are going to be calculating the temperatures in a composite bars. I hope you are able to understand the concept of the thermal stresses in a composite bar. Still, if you feel any difficulty, please put in the comment section so that I can reach you out. Thank you.